Hi everyone, it's my pleasure today to tell about our work, Dynamic Routing for Navigation in Changing Unknown Maps using Deep Reinforcement Learning. Our approach connects the benefits of reinforcement learning and the Markov decision process of the navigation task. First, I would like to introduce a bit about reinforcement learning, and then connect this to how we can let the agent learn to navigate in the real world. In this work, we are doing the navigation task. The goal of the agent is to start from any arbitrary location to find a trajectory to reach to the destination. First, let me show the result example of our agent navigating in the real OSU campus environment. As we can see, the agent starts from point A, passes by point B, and the target is point C. In the navigation process, the agent takes action according to the learned policy at each road intersection, like move forward, go backward, turn left, and turn right. During the whole process, the agent doesn't know the map and only see the RGB image, which is the first-person view observation. Our approach is reinforcement learning. The motivation of using reinforcement learning in this problem is because, unlike supervised learning or unsupervised learning, the reinforcement learning process is not based on the ground truth or the early experience. It's a self-learning process by interacting with the environment, which is a Markov decision process. Similarly, navigation is essentially an exploring and decision-making process. So, the trained agent exploits an action policy that rewards reaching the destination while interacting with the environment. Here, I would like to introduce a little about reinforcement learning. There are 5 basic elements for RL: agent, environment, observation, action, and reward. As we know, the most well-known implementation of RL is AlphaGo. So, how to learn to play the Go game? First, the AlphaGo agent takes observation from the environment, which is the chessboard. Then the agent will take an action based on what he sees. The action in this case is to put the white or black markers at one of the grid intersections on the board. The environment in this case is the opponent. After taking the action, the opponent will emit the immediate reward to evaluate this action, and also emit the next state. So by repeating this process, the agent gradually learned how to play the Go game, that is, how to generate the maximum cumulative reward. In our case, the environment is CampusNav, which spans the Ohio State University campus and the surrounding region with a total area of 4.5 square kilometers. While constructing the map graph, we extracted road network as a graph composed of edges and nodes at the intersections. The agent will learn to navigate in this CampusNav environment. The observations are the RGB images collected by iPhones placed on the top of the moving vehicle. The agent observes all 4 orientations, north, south, east, and west, to decide on an action. The raw image resolution is 640 by 480. We use the ImageNet pre-trained ResNet 50 to produce features as the input state to the Cryptic network in the training process. The agent does actions at the intersections, which are move forward, turn right, go backward, and turn left, based on what he sees, and interact with the environment. For example, if the agent chooses to move forward, it comes to the next state. If it reaches the goal, it will get 1 point. If not, minus 0.005 for a time penalty, and if collision, it will get minus 0.01. We update the Cryptic network according to this reward using temporary difference approach, and repeat this process until the agent masters the navigation policy. In the experiment part, we trained 2 kinds of agents. The first one is the single target agent. Single target agent is only trained to navigate to one destination, as we see the flag on this map. The other one is the multi-target agent. It is trained to navigate to multiple goals, specifically 4 targets in our experiment. So here we can see the navigation process to medical center, and then the DRIS lab. Here is the training process of 2 agents. As shown in this figure, the agent trained with multiple targets has stronger navigation ability than a single target agent with the same training episode. Our proposed algorithm for the RL agent is double-critic algorithm. This algorithm is based on Q-learning. In our model, we take the image that the agent sees as the state input. The target scene is specified by another image. We project them into the same embedding space, represented as embedding fusion input. The output is the action Q value and policy pi learned by the agent. The double-critic network is similar to the regular deep Q network. The critic network generates the Q value of current state ST given action AT. The target network generates the Q value of next state ST plus 1. The temporary difference between these 2 values should be the immediate reward R, and the critic network updates based on this temporary difference. The target network shares the same parameters as the critic network, but updated periodically. What different from traditional Q-learning here is we use 2 sets of critic network. That's because the shortcoming of Q-learning approach is it always prone to overestimate the Q value. Therefore, it towards finding a deterministic sequence rather than general solutions. Using 2 critic networks and always choosing the minimum of those values will avoid value overestimation problem. Another critical experiment for our method is dynamic routing task, which demonstrates the proposed agent's ability to adapt to the continuous changing environment. The change in environment are obtained by closing rows. The agent is expected to update the policy in accordance with the changes. Rather than relearn the whole environment, we focus on the constantly adapting the old skills to the changing map. To achieve this goal, our agent is firstly assigned a goal and trained for a single target navigation task. When map changes due to road closure, the agent quickly relearned policy with regards to the changes based on past experience. To sum up, our main contributions in this paper are navigation in long-range real-world environment, using only visual observations without other aids, and dynamic routing in changing maps. That's all. Thanks for listening.